In this video, I'm going to briefly discuss the different ways you could actually evaluate the different algorithms we've been talking about. These should be pretty straightforward. So the first idea, right, is basically of some sort of a deterministic evaluation. So that means is that ahead of time, I know what I want to run, right? So I'm saying that I have, I have basically schedule A, B, C, D, and then I have this set of say, okay, 100 processes, and I want to know basically how well they fare. Right, and so I could basically design some sort of a test set, right? And I'm going to just basically just say, oh, I know them all up front, right? So I'm not going to say that it's like some sort of a simulation where I'm getting jobs over time. I kind of know them in advance. This is nice because basically every algorithm can support this, right? So even algorithms that are just offline, they can support it as well. So I make kind of my list of all these different things that I might have having in my system, right? So I have a list of 100 things, right? Because I know them in advance and they're kind of fixed, right? I'll say that it's going to be a deterministic model, right? So I have 100 processes, each of them have a burst time associated with them. Let me see how good things do. So on the right, you can see I have kind of a test set, right? So I have here basically, I have 5 processes, right? So you can see here I basically have P1, P2, P3, P4, P5, and I know ahead of time basically how they're going to act, right? I know basically how long their burst is, right? And what I can do is if I know that in advance, right, is I basically feed it to my different schedules, right? So I can maybe do my, first come, first serve, over here, my short stops first over here, my round robin over here, right? So A, B, C. A, B, C, not A, B, A, B, B. That doesn't make quite much sense. A, B, C. So yeah, I can just have this stuff in advance, right? I can run them all, and from that I can compute whatever I want. So I compute my waiting time, compute my completion time, right? I'm kind of good to go. This is basically what we've been doing up until now. It's a pretty good method, right? But it's not always realistic, right? It's not always realistic. Generally, it requires some assumptions either about the distribution of data or basically how the ready queue behaves in the system. Overall, right, maybe we can do a little bit better. So the other way, which is kind of a simulation approach. So here what we're going to say is we can set up a system, right? We imagine we have a computer running. We're going to get an idea of, every so often, right? So basically what we do is do some stats analysis, right? We say, okay, on average, right, every 10 seconds a task is created, right? And that task is, has a mean time of 10 with a standard deviation of 2, right? You kind of have basically this distribution to show you, how much time does the process take, as well as how often does the process, how frequently does basically a process run, right? We have that information available to us. And from that, we can basically just do a bunch of sampling. So we can say, flip a coin, right? Do a random number generator, generate these random tasks, right? And basically what we do is have kind of this ad hoc system simulation where we're just spawning tasks, and tasks. And then we can run those algorithms against those ones that we spawn, right? And see how they behave. So we have here basically our kind of our guidelines of, how a process should act, right? So we expect it has these bursts and it has, this often, right? We generate from that basically some sort of a trace of this is how I think it's going to act, and then we can feed it right to our different algorithms, right? So we have all these 3 different choices here, right? And we kind of generate, right? And we can run through all of them. Ideally, right, we can move beyond basically doing this distribution thing, right, where it's like, oh, statistically I could see, it's, has this mean, this distribution, this standard deviation, so I can have, this size, this size, this size. We can move a little bit behind that and basically do a trace of a system. So we can basically hook up to an OS scheduler and basically say, for this day on this computer, write down everything that you do, right, all the processes that you encounter. And so if we had a trace, we could feed that to a scheduler as well, and we can analyze that and get a good idea basically of how long it takes to run for that set, right? And that would be kind of ideal because then you're kind of analyzing a real data set. So that's kind of our third approach, right? So we can basically either do random generation from a distribution, or we can do a trace, right? Or the previous slide was a deterministic approach. We just need everything in advance. So those are the 3 different ways we could possibly do this. The last kind of comment here on the slide is basically that the book has a little bit of a funny remark in that they say, oh, hey, if you want to do that tracing approach, don't mess with like a production system, which is kind of an obvious thing, right? You never change anything low level. Even just tracing is a big thing, right? You never change anything low level on a production level system, right? You do it on your development system, right? So on your development system, that's where you generate your trace. That's the thing you basically use to keep track of, which processes are running, right, and write those down so you can use those to benchmark your different scheduling algorithms, right? So don't mess with production. That should be an obvious, but the book still talks about it anyways. All right, so we have these different ways to kind of evaluate algorithms, just kind of as an aside, right? We're not really going to be using this too much in this course.